500 million years ago, a small marine animal solved one of the hardest problems in physics. How do you disappear? Not by hiding behind something, not by running away, not by making noise to distract a predator, but by becoming the thing you're already standing in front of. The cuttlefish has no bones. It has no armor. It weighs less than a paperback book, and yet it is effectively invisible to predators with eyes far more sensitive than ours. It does this using thousands of microscopic sacs in its skin, each one individually controlled by muscle and nervous system that warp its color, its texture, and the polarization of the light it reflects in real time for every observer looking at it from every angle simultaneously. Now, what if you could put that skin on a fighter jet? Not camouflage paint, not stealth geometry, not radar-absorbing coating. An active, living, computational skin that looks at what's behind the aircraft and projects it forward, so that any observer from any angle sees not the aircraft but whatever the aircraft is flying in front of. This is the blueprint for that system, and it is more complicated than the cuttlefish, but not by as much as you'd think. Let's start with something that sounds obvious but is worth saying out loud. Stealth aircraft are not invisible. They are radar hard to see. They are designed to reduce the energy that bounces back to a radar receiver when a radar beam hits them. They do this through three main techniques: angular geometry that deflects radar energy away from the receiver, radar-absorbing materials that turn radar energy into heat, and careful attention to any feature. An air intake, a weapon bay door, an antenna that might reflect energy back in the wrong direction. This works extremely well against radar. A B-2 bomber has a radar cross-section roughly equivalent to a large bird. An F-35's radar cross-section in its most carefully managed aspect is comparable to a golf ball. These are remarkable engineering achievements. But radar is not the only sensor that finds aircraft, and in 2026, it may not even be the most important one. Modern air warfare increasingly involves electro-optical tracking, targeting systems that use cameras and infrared sensors rather than radio waves. An F-35 is not hard to see with a camera. Its exhaust is not hard to track with an infrared sensor. Its distinctive silhouette, recognizable to any trained observer, is visible to the naked eye from several kilometers at altitude. And then there's the more recent problem: drone-launched optical seekers. A small drone carrying a high-resolution camera, flying in a surveillance pattern at medium altitude, is not looking for radar returns. It's looking at the sky. And against the sky, any conventional aircraft, stealth or otherwise, is a dark silhouette. Stealth, as currently understood, handles one part of the detection problem, the radar part, the optical part, the infrared part, the electro-optical part. These remain largely unsolved. A fighter aircraft at altitude is optically about as stealthy as a hawk, which is to say, not very. The system we're describing today is not a replacement for radar stealth. It is the missing layer. The one that handles visual detection. The one that the Cuttlefish solved 500 million years before we started thinking seriously about the problem. The Cuttlefish's basic unit is a chromatophore, a pigment sac about 50 to 500 micrometers across, controlled by a direct muscle attachment. Each one is a pixel. The Cuttlefish brain updates all of them simultaneously, constantly, based on visual input from its eyes and photoreceptors in its skin. Our equivalent unit is a micro-faceted photovoltaic cell. It is, conceptually, trying to do what the chromatophore does. Be an individually controllable pixel in a skin that collectively produces an image. But it has to do it differently because it can't use pigment. It has to emit light, not reflect it. The cell is half-octagon shaped, not flat, but faceted, like a tiny cut gemstone. The shape matters enormously. Each flat facet of the half-octagon is oriented at a slightly different angle. This means the cell can emit light in slightly different spatial directions depending on which subpixel within it is active. The result is that a single cell can send different images to observers looking at it from different angles, simultaneously. Think about a lenticular print, the novelty cards where the image changes depending on what angle you look at it from. The tiny lenses on the surface route different colors to different angles of view. The micro-faceted cell is doing the same thing, but computationally in real time, and at a resolution the lenticular print couldn't dream of. The cell needs to do 4 things simultaneously. First, sense what's behind the aircraft, what the background sky looks like from the direction that would be the view if the aircraft weren't there. Second, identify which angle each observer is looking from. Third, emit the appropriate background image toward each observer at the correct angle. Fourth, power all of this, ideally without drawing on the aircraft's main power systems. The material for the cell body is gallium arsenide, GaAs, for the rigid fuselage zones, and a perovskite or organic photovoltaic hybrid for the flexible zones around wing roots and control surfaces. Gallium arsenide is a semiconductor with extremely high electron mobility. Its refresh rate, how fast it can change what it's displaying, is sub-millisecond. That matters because the aircraft is moving at high speed. The background changes constantly. The cell needs to keep up. And there are a lot of them. A fighter-class aircraft has a fuselage surface area of roughly 300 square meters. At 300 pixels per inch, roughly the pixel density of a modern smartphone screen, 300 square meters of fuselage requires approximately 41.8 billion active cells. $41.8 billion. We will come back to what that number does to the computational requirements. For now, That is the scale of the system. 41 billion individually addressable pixels, each one a 60 to 80 micrometer half-octagon, each one tracking multiple observer angles simultaneously, each one refreshing sub-millisecond. The Cuttlefish manages about 10 million chromatophores. We are proposing something 4,000 times more complex. But the Cuttlefish is working with slow biological muscle tissue. We are working with semiconductors. The physics allows it, even if the engineering is daunting. The obvious objection at this point is 41 billion cells, each one an independently functioning microscopic unit, 60 to 80 micrometers across. Is that even manufacturable? It is. And the reason it is has nothing to do with building 41 billion cells one at a time. Nobody builds chips one transistor at a time either. The key is that you don't craft each cell individually. You grow the entire array simultaneously. The technology is called monolithic semiconductor integration. It is the same photolithography process used to manufacture computer processor chips. A silicon or gallium arsenide wafer is coated with a light-sensitive chemical. A precise pattern is projected onto it using ultraviolet light. The chemical hardens where the light hits it. The rest is etched away. Repeat this process with different materials and different patterns, layering them, and you build up a three-dimensional circuit structure across the entire wafer surface at once. To put the scale in context, a 50 to 80 micrometer cell is, by semiconductor standards, enormous. The transistors inside a modern processor chip are measured in single-digit nanometers, a nanometer being 1,000 times smaller than a micrometer. Modern microdisplay technology, the kind used in high-end virtual reality headsets, already routinely manufactures full-color micro-LED pixels under 5 micrometers in size. Our cell is 10 to 16 times larger than those pixels. We are not pushing the boundary of what photolithography can do. We are working comfortably within it. At 50 micrometers, a single bump cell is large enough to contain an entire microscopic computer circuit, a set of light sensors, and a set of light emitters, all within its borders. The size is not a manufacturing constraint. It is a choice driven by aerodynamics. 60 micrometers is the number the boundary layer allows. It happens to be a number semiconductor fabrication finds easy. Each cell is what engineers call an active matrix smart pixel. The key word is active. Instead of being wired individually to a central computer, which would require 41 billion separate wires and is obviously impossible, each cell is bonded directly onto a CMOS backplane. CMOS stands for complementary metal oxide semiconductor. It is the same transistor technology that underlies every modern computer chip. The CMOS backplane acts like a high-speed digital highway running underneath the entire skin. It sends out a single mass data signal across the whole surface simultaneously. But here is the elegant part. Each cell has its own unique digital address. Think of it like an IP address, the kind every device on the internet uses to identify itself. The microtransistors inside the cell intercept only the data addressed specifically to them. They process it locally. They execute the instruction locally. No central processor needs to individually command 41 billion cells. The skin commands itself, cell by cell, from the bottom up. Now, how does a cell this small actually display anything? It does not display a picture on itself the way a television pixel does. A television pixel sits at a fixed position and contributes one dot to a flat image viewed from a fixed distance in a fixed direction. The bump cell does something entirely different. It is a directional vector light projector. On the angled faces of the half-octagon structure, we embed sub-micron micro-LEDs, light-emitting diodes so small they sit below the size visible to the naked eye. Because each face of the octagon is angled differently, the light from each face travels in a different direction. The left facet fires left. The right facet fires right. The upper left facet fires upper left. Now consider an observer standing 1 kilometer to the left of the aircraft. Their eye captures only the light traveling in the direction they are standing, the beams coming from the left facets of millions of cells across the entire fuselage simultaneously. Their brain blends those millions of tiny directional light beams together into a single, cohesive, high-resolution background image. Not a patch, not a blur, a complete seamless picture of the sky that should be behind the aircraft from their exact position. At the exact same moment, an observer above the aircraft, a satellite camera, another pilot, sees only the light from the upward-facing facets. A completely different image, projected simultaneously. Same skin, same instant, different picture for every angle. By altering which facets are illuminated on each cell, the system can project an entirely different background to an observer on the ground and to an interceptor pilot flying above, at exactly the same time. This is the vector light trick. The skin is not a screen. It is a directional broadcast array. Here is the question that the vector light explanation leaves open. If the left side of the aircraft is projecting what the sky looks like from the right, how does the left side know what the sky looks like from the right? Something has to capture that background image. Something has to be the camera. The answer is that the skin does not need separate cameras. Every single bump cell operates as a two-way optical node, simultaneously a projector and a sensor. The same microscopic architecture that emits light also captures it. On the flat faces of each half-octagon, the subpixels alternate between two types. Half are light-emitting diodes. They fire light outward in their specific direction. The other half are silicon photodiodes, the same raw material used in smartphone camera sensors. They capture incoming light from the same specific direction. The emitters and sensors are interleaved across every facet of every cell across the entire fuselage. This means the right side of the fuselage is simultaneously projecting what is behind the aircraft toward observers on the right, and capturing, through its photodiodes, the background environment in front of the right side. That captured data routes through the internal network to the left side, which projects it toward observers on the left. The aircraft is not hiding the sky, it is routing the sky through itself from one face to the other. But there is an obvious problem. If a cell is emitting light bright enough to match the daytime sky, which is very bright, how do the photodiodes in the same cell capture anything? The emitted light would blind the sensors immediately adjacent to it. The solution is temporal multiplexing. The skin does not stay on continuously. Instead, it pulses at roughly 1,000 cycles per second, 1,000 hertz. A speed completely imperceptible to the human eye, which cannot distinguish flicker above about 60 cycles per second. Within each 1,000 hertz cycle, the cell divides its time. For 850 microseconds, the micro-LEDs are active, projecting the background image outward. For the remaining 150 microseconds, the LEDs shut completely off. The photodiodes open. They capture the incoming background light with no self-generated glare contaminating the image. Then, the cycle repeats. From the perspective of any observer, human eye, camera, missile seeker, the projection appears continuous. The pulsing is invisible. What the observer sees is a smooth, unbroken background image that perfectly matches the sky behind the aircraft from their specific angle. The captured background data does not go to a central server for processing. It routes immediately along high-speed fiber optic lines embedded within the airframe structure. The same structural composite layers that form the aircraft's skin, straight to the opposing surface. The local CMOS backplane on that surface converts the incoming light data into directional vector instructions for its micro-LED facets in real time. There is no perceptible delay. The aircraft is, in effect, a high-speed digital lens. It takes light in one side and passes it through its own structure to appear on the other side, faster than the eye, faster than any camera, faster than any targeting system can detect the substitution. Here is the problem that almost kills this concept before it gets started. You cannot put bumps on an aircraft that flies at high speed. Or rather, you can, but you will pay for it in drag, and drag costs fuel, and fuel limits range, and limited range is tactically disqualifying. The physics of boundary layer flow is complicated, but the important part is this. When air flows over a surface at high speed, there is a thin layer of air immediately adjacent to the surface, the boundary layer, that behaves differently from the free stream airflow above it. Within the boundary layer, closest to the surface, is an even thinner region called the viscous sublayer, sometimes called the laminar sublayer, where the flow is smooth and ordered regardless of surface roughness. At Mach 0.8 at 10,000 meters altitude, typical cruise conditions for a high-altitude surveillance or intercept aircraft, the viscous sublayer is roughly 20 micrometers thick. The buffer zone above it extends to about 80 micrometers. A 50 to 80 micrometer cell sits right at that boundary. It pokes out of the viscous sublayer and into the buffer zone. It does not penetrate the fully turbulent outer layer, the layer where bumps cause serious drag penalties. The drag cost of a 60 micrometer cell at Mach 0.8 is approximately 1 to 3% of skin friction drag. Not zero, but manageable. Within the envelope of engineering tolerance for this class of aircraft. Here's the important number: 1 millimeter. If the cell were 1 millimeter tall instead of 60 micrometers, 16 times larger, the drag penalty jumps to 10 to 15%. The cells become visible to radar as scattering elements. The entire concept breaks down. 60 micrometers is not an arbitrary design choice. It is the load-bearing specification, the number that makes everything else possible. The aerodynamics problem gets harder above Mach 1.0. In the transonic and supersonic regime, the boundary layer dynamics change. Shock waves form over surface features. The drag penalty for the faceted cells increases sharply. At Mach 1.2, the drag penalty could reach 10 to 15%, operationally significant. The solution is retraction. The cells fold flat against the fuselage surface at supersonic speeds, eliminating the drag penalty. The retraction mechanism uses piezoelectric actuators, materials that deform when an electric current is applied, that can move the cell from extended to retracted in microseconds. The trigger is the throttle threshold. When the aircraft crosses Mach 1.0, the actuators fire, the cells flatten, the system goes dark. This creates an operational constraint that the Cuttlefish doesn't have. The Cuttlefish is always invisible. The invisible jet is invisible below Mach 1.0 and conventionally visible above it, which means the system is designed for subsonic and high subsonic operation, the regime where long-duration surveillance, interceptor patrol, and high-altitude reconnaissance typically occur. It was not designed for a supersonic dash into enemy territory. It was designed for the hours spent holding position at altitude, watching, waiting. The mission profile where optical detection is the primary threat and supersonic speed is not the primary requirement. That is not a flaw. It is a design choice, and it is the right choice for the operational context the system was built for. The hardest part of what the Cuttlefish does is not changing color. It's knowing who is watching. A Cuttlefish facing a predator has one observer to fool. It can orient its skin pattern toward that predator and maintain it. A high-altitude aircraft has potentially hundreds of observers, ground-based radar operators, missile seeker heads, drone-mounted cameras, satellite sensors, infantry soldiers with binoculars, each looking from a different direction, each requiring a different image projected back at them. Each cell on the fuselage surface receives multiple lines of sight simultaneously. Cell number 4 billion something on the upper left fuselage might be in the line of sight of a ground observer to the south, a drone camera to the north, and a satellite sensor directly above, all at the same time. It needs to show each observer the correct background for their specific angle. The half-octagon facet geometry handles the multi-angle emission, each facet pointing at a slightly different direction, routing different images to different viewing angles. But the system has to know which angles are actually occupied by observers before it can route correctly. This is where threat detection integrates with optical projection. The aircraft's radar warning receivers, missile approach warners, and electro-optical sensors collectively build a threat picture, a map of known observers and their positions. The projection system uses that map to prioritize which angles get full resolution projection and which get a simpler, lower power global sky gradient. This is called foveated rendering. Virtual reality headsets use it. Your eye can only process fine detail in the central 2 degrees of your visual field, so a smart VR system renders high resolution where you're looking and lower resolution in your peripheral vision, saving enormous computation. The invisible jet uses the same principle spatially: high resolution toward known threats, low power gradient everywhere else. The vulnerability in this approach is the passive observer, a soldier in a ditch with binoculars, not emitting any signal, a civilian camera network, a passive optical satellite. Observers who are not emitting anything the threat detection suite can pick up. These observers are not on the threat map. The system cannot route full resolution projection toward them because it doesn't know they're there. This is not a fatal flaw. At operational altitude, above 25,000 feet, the number of passive ground observers with line-of-sight access to the aircraft at useful resolution is small. The sky above 25,000 feet is the simplest background on Earth, a smooth blue gradient that changes slowly. The global low-power mode at altitude is projecting a smooth blue gradient. It does not need precision to be effective, because the background itself is not complex. At low altitude, where the background is trees, buildings, roads, terrain that changes every 50 meters, the passive observer problem becomes much harder. The global mode would project a generic terrain approximation that might fool a casual observer, but would not fool a trained one at close range. This is why the system is optimized for high-altitude operation. At altitude, the sky is forgiving. Near the ground, it is not. Sensing the background, tracking observers, computing the correct projection, emitting the right light at the right angle, all 41 billion cells, all the time. How do you power that? The short answer is, you don't power all of it all the time. And the long answer is a story about the difference between what the system needs in theory and what it actually requires in practice. In theory, illuminating 300 square meters of fuselage at full projection intensity requires somewhere between 600,000 and 1 million watts in full daylight.